Welcome back to lecture 9 in GRA 6036. This is the second video, and we'll now move ahead to something that appears to be more pressing than coin tossing. So these days people are naturally talking about the possible effects of the measures enacted by the states around the world to counter the spread of the COVID-19 virus in their populations. And of course, at the present time, it's hard to say anything clever simply because people lack the data to say anything. We're in the middle of this crisis, but we can imagine that a few months ahead in time, we'll have the data and we can start to say something about the possible effects of the different measures. So, for example, let's say you're interested in the effect of closing all the schools. So, well, to say something about that, we need data. So let's suppose that we're in August 2020, and we have y1 up to yn. So these are data points from n different countries, and each yi is the share of the population infected with the COVID-19 virus. So this is the number of infected people divided by the population size for country I. Okay, so we have these data. So for this to be well defined, it needs to be the number of infected people over a certain time interval, of course, and so that's something we have to choose in August. So we also have data on whether or not the schools remained open or were closed during this time. So let's say that's let's call it xi, which is then an indicator taking the value 0 if the schools were open, and taking the value 1 if schools closed. Okay, so now to say something about the possible effect of x on y, we could split this into two groups and then compute the mean of the y's for both groups. But here, since we are doing linear regression, we'll formulate this as a regression problem. So to connect x and y, we can say that, well, here's our model of what we think the world looks like. So there is yi is equal to beta 0, beta 1 times xi plus a mean 0 noise term for each of our n countries. Okay, so this is the regression model, and in this model, beta 0 and beta 1 are unknown parameters, just as P was an unknown thing about the coin. So, to say something about the effect of x on y, we need to know something about these parameters. So, what we'll do is that based on our data, so now we have data x1, y1, for country 1 up to xn, yn for the nth country. And we can use these data to estimate these parameters. So we'll do least squares estimation, which means that we'll find the values of beta 0 and beta 1 that minimizes this function, and you should now be able to differentiate with respect to beta 0, beta 1, and find find the minimizers of this function, and know that that is minimizing this function is what the lm function in R is doing for you. So if this little y here is a vector in R consisting of y1 up to yn, you write lm y tilde x, and this function will then return you the minimizers of this function. So that's what that's our estimators, and what we denote by beta 0 hat and beta 1 hat. So these are now the least squares, the ordinary least squares estimators, the ULS estimators. So these are ULS estimators. Okay, and I mean, since we're supposing that we are in August, we have this data, we feed this data into R and we run the LM routine. Then we get these estimates. So let's say that the numbers that we get are beta 0 hat is equal to 0.43 and beta 1 hat is equal to minus 0.08. Okay, so now based on these numbers, we might be tempted to conclude that, well, closing the schools did have an effect on the share of infected people in the population, because this is a negative number. So we can say, well, closing the schools decreased the number of infected people by 8 percentage points. But we would then conclude, a bit too quickly, because, and here the reasoning is the same as with the coin tosses, because here, let me now go back to the coin tosses. Getting this sequence, we wanted to conclude, well, we did conclude that this null hypothesis is probably not true, because the probability of obtaining this sequence under a hypothesis that this is true, or under the assumption that this hypothesis is true, was small. But I mean, this 3% chance of getting, I mean, there is still a 3% chance of getting this sequence, assuming that the null hypothesis is true. So it's not impossible. It's just that the probability of obtaining this sequence is really small. So we'll ask the same question in this regression problem. We want to ask, well, let's say that in reality there is no effect of closing the schools or not on the share of infected people, which means that no effect here means that the true beta 1 is 0, or you could say, well, the correct model for the world is just one in which yi is equal to beta 0 plus some noise. But so if this is the null hypothesis, while the alternative hypothesis is that beta 1 is not equal to 0, the question is, well, what's the probability of getting this number if this is the truth? And so to conclude that this number, well, that beta 1 is truly not equal to 0, that there is truly an effect of closing the schools, then we have to know that this number is that the probability of obtaining this number, if this is true, is small. So that reasoning is just the same as with the coin tosses. And in the next video, I'll come back to how we are to do this.